Yes, thank you very much. Too bad I couldn't come again. Yeah, I had to go to Warsaw for a PhD defense, then to Germany. And then I got, during the travel, I got kind of sick and I couldn't make it to Italy again. Okay, well, thanks anyway for having me. And yeah, my name is Krenn, and I would like to talk briefly about how we can use computers to get new ideas. How can we use artificial intelligence to inspire new ideas? Kind of like a artificial muse that we can use. And I will show this in two different ways, so two concrete different ways. And the first thing is how we can use computers to design new quantum experiments and get new understanding out of it. And the second one is how we can predict and suggest personalized research directions through a huge amount of scientific literature and natural language processing. And in the end, I will show them a slightly broader picture of this whole question. Okay, so this whole topic has started a few years ago during my PhD. So I did a PhD in the experimental quantum physics group, and the goal of this group was to investigate quantum entanglement, so explore quantum entangled systems and their properties. And at that time, we wanted to observe some new type of high-dimensional multi-particle entanglement. So let's start with the simplest thing. What is entanglement? So you have the simplest form of entanglement that you can imagine consists of two particles that are entangled in 2 degrees. For instance, you can have 2 photons, where both photons are either red or both photons are green. And before you measure them, they don't have a well-defined color. Only when you measure the first one, also the second one gets this color. And this state has been investigated for the last 50 years. So this was the first time explored experimentally in the 1970s. Now, if we want to make our system more complex, we can add a number of particles. For instance, now we could think about having 3 particles where all 3 particles are red, all 3 particles are green. And again, only if you measure one particle, it gets its well-defined color, and then all of the other particles also get their color. And this is called the GHZ state after the inventors Greenberger, Horn, and Zeilinger. And increasing the number of particles in entanglement is a very important resource for quantum computing. But you could also increase the complexity in a different way by keeping 2 particles and increasing the number of dimensions that you entangle them in. For instance, you can have now 2 particles where both particles are red or both particles are green and both particles are blue. And this state is called high-dimensional entanglement, and it's very much investigated in quantum communication because you can store more information in one particle that you can transmit. And it's also investigated for roughly 20 years now. And at that time of my PhD a few years ago, we wanted to investigate a system that is high-dimensionally and multi-particle entangled. And these states have never been investigated experimentally, so none of its properties have ever been observed before. And even theoretically, there have been many open questions, and it seems that there are many interesting properties that those states can have. And so our goal was to create this state and observe some of those properties. Now, the first thing that you need when you want to create a state is you need to so the first thing that you need to do when you want to observe the properties of the state, you need to create a state, and for that you need to know what is the experimental setup. And so usually when we come up with an experimental setup for a quantum system, it works like this. We go to the blackboard or to our pen and paper, and we use our experience and intuition, and rather quickly can write down some experimental systems. And that has been how experimental setups have been designed in this field of quantum optics for, well, since its beginning. But surprisingly, at this point, this was not possible anymore. So we wanted to create this state, and several of my colleagues and me, who were experimentalists and theorists, we wanted to come up with an experiment that can create this state. But we failed. For several weeks, we were not able to find any feasible experimental configuration that could create anything like this. And that was completely unheard of in this kind of community. And I thought that's very strange, and maybe we need to try to do something different. And then what I came up with at this point was a computer algorithm that can kind of automatically design such experiments that produce those states. So, and let me show you briefly how such a computer algorithm works. So in this case, we start, or the most important thing is that we start with an experimental toolbox. And in this toolbox, we have all of the experimental elements that we have in our laboratory. For instance, laser or beam splitter, or phase shifters, detectors, nonlinear crystals, and so on. And now the algorithm in the beginning starts to assemble those elements in a random fashion. It takes a virtual optical table and puts those elements. And then it makes a few sanity checks. For instance, does the detector ever see a photon? If no, it's probably not a very good setup. And if it satisfies all of those sanity checks, the algorithm computes them, simulates the computation of this setup. And if the setup produces the state that we wanted, it's reported to the user and everyone is happy. But it's also then simplified, and the experiment is added into the toolbox. And in that way, the toolbox gets larger and larger over time with more useful components. And in that way, the system learns to build more complex and more clever experiments over time. So in the next iteration, it can already access these more complex systems in the toolbox and use it as building blocks for the next setup that it analyzes. And the simple algorithm, this algorithm was not only simple, but actually it did exactly what we were hoping for. I ran it overnight, and so I programmed it and ran it overnight, and in the morning I really found a solution.txt file at my desktop that shows to me that it found the experimental setup. And it found actually experimental setup that all of my colleagues and me were not able to find for many weeks. So this was a very good day, and we were then having actually a feasible experiment that we can build in our laboratories. And actually this experiment that the computer has suggested that we humans were not able to find was then built over the course of the next 3 or 4 years by 2 of my colleagues. And with that, we were able to create the state that we wanted to create in the beginning and observe some of its properties. And of course, this was very interesting for us, and we try to apply this algorithm also to several other systems. And in many cases, the algorithm was able to solve questions that we ourselves were not able to solve. We were then able to build up new quantum hardware and quantum measurement, quantum measurement tools and quantum transformations and so on. Very recently, we have applied this algorithm also to superconducting quantum computers, specifically to the IBM superconducting quantum computer, because they were exploring also high-dimensional or higher levels of excitations, basically beyond the level 0 and 1, they were also exploring the level 2. But for this level 2, all of the gates were not very well known how one can use them to do something useful actually. And then by applying this simple algorithm, we were able to find the first circuit that can create also here in the superconducting system a high-dimensional multi-particle entangled state, and we then run it at the IBM quantum computer, and for the first time generated also the high-dimensional multi-particle entanglement. So this was not only useful, but this also has led to something really interesting. And the thing that I find even more interesting than the experiments themselves, namely, it was able to give us new ideas in this context of quantum hardware. And that worked in one case in the following way. So I was very happy with the algorithm exploring this three-dimensional three-particle entangled state. Then I thought maybe I can let the computer explore much larger systems, so much higher dimensional entangled systems. So I copied this code to some of the unused computers in our lab and ran it. And after a few weeks, I came back. And actually, when I ran it, I used some specific resources to create the quantum states. And with those resources, I thought, and I was pretty convinced, that the algorithm will not be able to surpass some certain level of entanglement, so that it cannot create entanglement larger than some certain numbers. But when I came back after a few weeks and looked at the log file, there was actually one solution that went far beyond of this limit that I thought that exists. So the first thing that I thought is that there are some bugs in my code, but then I checked these solutions, and actually it did produce exactly what it was saying. It produced I think 12-dimensional entangled system, while I thought that the limitation needs to be 9, so that nothing can go beyond the limit of 9. So then I was, of course, very, very curious. Why can it go beyond my limitation? I didn't understand how that would work. And so I looked at the solutions for several days, actually, I think for some weeks, because the solution was extremely complicated. And then after a few weeks, I actually found out what the computer was doing. It was completely implicitly using a technique that was invented in the early 1990s in a completely different context. And it was using this technique to generate very high-dimensional entangled systems. And it did that in a way that no human has ever thought of. Actually, it was able to create scalable sources for high-dimensional entanglement. So these are some examples which I will explain one of them. So the idea was that if you look at this third example where you have these three gray blocks in a row. So each of those gray blocks produces a photon pair, okay? And let's say this photon pair is created in the 0 mode, okay? So when it's produced in 0, 0. So both photons are 0. Now these red blocks or these red lines, they mean mode shifters. They add a +1 to the mode. So if the first crystal on top creates a photon pair, it produces 0, 0 because it doesn't go through any of those red blocks. If the photon pair is produced in the second crystal, it goes one time through these red lines and then goes to the detectors. That means it is shifted to 1, 1. If it's produced in the third crystal, it's shifted to 2, 2, and then in the lowest crystal, it's shifted to 3, 3. So if we can create this system in a coherent superposition, what it gives out is a superposition of 0, 0, plus 1, 1, plus 2, 2, plus 3, 3. That means that's a scalable, or that's a 4-dimensional entangled system. And you can easily see how to increase the entanglement of the system. And this is just the very simplest special case of what the computer has found. Actually, it has found something much more complex for multi-particle systems. But the cool thing was, as soon as I was able to understand what the computer has found, I was immediately able to generalize it to many other cases. And actually, we have then written an article about this result, and we were able to get it published in PRL. And the cool thing was that the main conceptual and creative contribution did not come from any of the authors. The main idea came from a computer who was tasked to explore a high-dimensional space. So that was kind of cool. Unfortunately, we didn't put the computer as a co-author, but we added it in the acknowledgements. So this later we found out why this system that the computer has discovered works so well, and that's because in a way it is directly related to some graph theory representation of quantum optics that was not known before. And only when we then further analyzed the solutions of the computer, we saw that actually what is standing behind it is a new way, a new total abstract way to think about those quantum experiments. So now we had a link where we take a question in experimental quantum optics. We can translate it to graph theory. We solve the tools of graph theory. We solve it with the tools of graph theory, and then translate the answers back to quantum optics. So that bridge was also in a way inspired through the solution from the computer. And these links have given us some new ideas about quantum computation, because much is known about complexity classes of certain problems in graphs, and we know now how to encode those problems with very high complexity classes. So we can now basically solve with quantum experiments some of those very difficult questions in graph theory. And some very early experiments that followed those recipes has recently been performed. This is one example of an on-chip device that performed one of these experiments that was inspired from the solution of the computer. So now we have seen that we can get actually new ideas through AI, through computers. But the problem was that the solutions of the computer was extremely complicated, and it took me, I think, 2 or 3 weeks to understand what is going on. So the question is whether we can make new algorithms that are that give us the solution in a much easier way. And that is what we have shown 1 year ago. So we designed a new algorithm that basically uses this graph-based representation at its core. So instead of working in the domain of actually experimental optics, it works now in the domain of graph theory. And here we use the idea that every experiment that we can build in the lab can be translated to a colored weighted graph, and each of those colored weighted graphs can be translated to an experiment. And here the idea of vertices is they stand somehow for the paths of photons, so the locations of photons. Edges between two vertices means a correlation between two photons. And the column stands for the photonic mode number, for instance, mode 0, mode 1, and so on. And the weight of these edges stand for the amplitude or the strength of this correlation. And with this, you can basically describe every experiment, and you can translate this graph also back to every experiment. And the cool thing is here that we can use that we can compute basically arbitrary objective functions directly as functions of the weights of the graph. For instance, if we are interested in computing the fidelity or if we want to design an experiment for a certain quantum state, we will compute the fidelity to this quantum states as a term or as a function of the weights of the graphs, and then we can use advanced gradient descent methods to actually find the correct settings of those weights. So our algorithm starts usually with a complete graph, because a complete graph, a weighted complete graph, is the most general thing that you can build in an experiment. And the algorithm then uses those objective functions and maximizes them by changing the weights of this graph. So then we have a very large settings of weight combinations that give us the solution. But this is usually not very useful for us here, because it's basically impossible to understand any solutions with dozens or hundreds of weights. So what we also implement, that's the very important part, is the topological optimization. So at each step when the algorithm says, okay, I optimized now my parameters, we try to reduce the number of edges, such that in the end we get a very simple solution. So basically you can think about this as searching for the conceptual core of the solution in the graph. And this is what we try to extract from the solution. Try to extract basically the concept that leads and that is necessary for producing this solution. And when we get this conceptual core, we can usually very easily see why it works. Usually we just look at it and basically immediately know why that solution works. And I can give a very quick high-level example of how it looks like. So one of the important questions in quantum optics or in experimental quantum physics in general is, how do you generate a state basically deterministically? Now in quantum optics, there are some problems, like in every other platform, but here one of the problems is that the main sources that you use are probabilistic. That means you don't always get the state that you want. You basically get it with some probability. But now you can you could think about having a system that has a few trigger detectors, and if those trigger detectors give you a click, then you know for sure that you got a certain quantum state. And that is called heralded entanglement. So again, the idea is you have a few detectors, and if those detectors fire, then you know that from two other outputs, you have 100% sure this correct quantum state. And finding heralded entanglement is usually very complicated. And in our case, we wanted to solve this question for an unsolved problem. So we wanted to get heralded three-dimensional entanglement. So when a few detectors click, we are 100% sure that the output is 0, 0 plus 1, 1 plus 2, 2. So we start with a certain initial graph, and within maybe a minute or so, it gives us the solution. And the solution is basically very simpler, is very few number of edges. And when I saw the solution, within a few minutes, I understood why the solution works. So before, there were no solution. I was not able to come up with any idea how one could build something like that. But when I saw the solution, I immediately knew what's going on there. So the computer was trying to get around one of the biggest problems, namely when you have no output of your system. That means when all of this trigger detector fire, you have no output. That's basically you create a vacuum, and that is the thing that you want that does not happen. So what the computer came up with, it created this vacuum twice with a different sign. So it was able to destructively interfere these vacuum contributions. So by destructively interfering them, it was clear that everything that comes out is the correct quantum state, is not a vacuum at least. So this was basically never described in the scientific literature, that you can have destructive interference of vacuum. And as soon as I saw this solution, I was immediately able to generalize this idea to many other systems. So I was immediately able to use these concepts in other contexts without needing to perform any more computation. So actually, I learned something from the computer that I can now use to solve questions by hand. And that shows that I clearly got some new understanding from this machine. Okay, so I would switch gears now and stop with this first part of quantum experimental design and come to another question where we also can get some new ideas or inspirations from the machine. So here we can step back and think about how can we make, or what is the big question that we want to solve. And the big question is, we want to make a computer that can inspire surprising and interesting ideas. But for that, we need to know, what does it mean to be surprising and interesting? And this is obviously very subjective and depends on our previous knowledge. So now our question is, how can we get this previous knowledge into the computer? And you could think about large language models and so on, but they are very difficult to work with, and they are known to have huge problems with logical reasonings and so on. So at that time, we took a very different approach. That approach was basically inspired by computational sociologists and computational biologists. So what they have done, and what I then also did in quantum physics, was we were building up a knowledge network, an evolving knowledge network that kind of contains a lot of information of the scientific literature. And this works in the following way. So we built up a semantic network or a knowledge network. And here every vertex stands for a scientific concept. And two vertices are connected when they are investigated together in a scientific paper. And this is basically the knowledge network that we want to build up. So for that, what we need is, of course, a concept list and large amount of scientific literature. And the concept list, I used Wikipedia and quantum physics books and natural language processing on archive papers, and got a list of roughly 6,000 concepts in quantum physics. So they are now the nodes of my network. And the connections are drawn when when one paper investigates these two concepts together. And for that, I use the archive, articles, and all papers that have ever been published by the American Physical Society. So here, basically, they are able to provide the metadata for all of the articles, and that was sufficient for me because I was only working with abstracts and titles. So, and here when we use this 750,000 articles, we basically get an evolving knowledge network over time. So over the last 100 years, because those edges, all of them have a timestamp when they are formed. And so you can imagine that you have an evolving network from 1920 onwards to 2017 in this case, for instance, or 2020. So now, of course, when we have an evolving network of the past, we can ask whether it's actually possible to predict something about the future of quantum physics or quantum physics research. So basically, the question is, can we predict what scientists will do in the next 5 years that they have not done yet? And reformulated in network science, we can ask which unconnected pairs of concepts, so unconnected means they have never been investigated in a paper together, which of those unconnected concepts will be investigated in the next 5 years? And of course, we can use neural network to answer that question. Basically, we can use now our knowledge network of 2017. We put in unconnected vertex pairs into the neural network, and the neural network needs to predict whether this unconnected pairs will be connected 5 years later. And for 2022, we have the result. So we have a supervision signal. So we can supervise this training process. So in the end, we have a neural network that can predict 5 years into the future. So afterwards, we can, of course, use the data of 2022 to predict what will scientists work on until 2027 that they haven't worked on so far. And surprisingly, the quality is quite high for this prediction. So it's quite one can predict those qualities to a very high degree. So I have used to measure this. I've used the metric of area under the curve of the ROC curve, and basically one can interpret this as what is the percentage that you predict that you would rank one instance that was connected higher than an instance that was not connected. So what is the probability? And in my case, it was around 80%. So with 80%, I know when you give me two concepts, which of them will be connected and which of them will not be connected. And this is, of course, very interesting if we have a field that is exploding, where there are a lot of scientific papers. For instance, in the field of AI and machine learning, the number of papers are growing exponentially. So no researchers can read anymore what the field is working on. So we need to kind of restrict ourselves to very small domains, and it's very difficult to go outside of this domain. So one of the ideas is to actually use those predictions and personalize them. For instance, one can use as one of the concepts list that is connected. We can use the concept of one individual scientist and then predict what the field will do. And we can also introduce something like what the field will do, but that is kind of unexpected. There's some network theoretical measures to do that. And recently I've created an AI competition to solve this task with a prize money of 25,000 euros. And there were roughly 40 contributions, and people came up with incredibly creative solutions to solve this task, and were able to go up to 90 or beyond 90% prediction quality of what will happen in the future. And if you change this question slightly, if you ask the question, what is not investigated now but will be investigated not only in one article but in at least 3 articles in a span of 3 years or 5 years, this question can now be answered basically deterministically with beyond 99.9% quality. So we basically found some very weird deterministic patterns in scientific research. And we have just submitted the article about this to arXiv. It will be online in a few days, I guess. So now if we have personalized suggestions, the most interesting extension that I can think of is actually introducing an additional metric of success. For instance, not only predict what will happen, but also predict what will be very influential. So for instance, what might have very high sedation rates, high expectation of sedation rates. So imagine a machine which gives you suggestions for topics that have never been investigated together, that are very close to your own field, and where the machine tells you, I predict that this connection will have very high sedation in the future. That would be really, really interesting, I guess. Okay, but we're not there yet. Soon, maybe, yeah, maybe soon. Okay, now let me step back and look at the bigger picture of generally how we can find or how we can use AIs to inspire new ideas. So we recently wrote an article on a slightly more general topic on how we can get scientific understanding from AI, and it was just accepted in Nature Review Physics. And one of those ways how we can get understanding is by using computers as a source or resource of inspiration. And we collected 5 ways how this is possible. This could be done. There have been some steps into these directions and what would be possible. So the first one is anomaly detection, where 2 weeks ago when I've been there were several talks for astronomy and high energy physics, where people try to use some type of machine learning to do anomaly detection. So these anomalies, if they are true in the data, they are usually a thing that scientists will look at, and that inspires them to change the direction of research towards those new outliers. A different way is using a large collection of scientific literature. And I've just shown you one way. There are several other ways how this could be done. For instance, there's a work in chemistry where people used autoencoders to encode the abstracts of many chemistry papers into a large latent space, and then they found out that in this latent space, it seems that the tool predicts that some materials have certain properties that have never been mentioned anywhere in the scientific literature before. So they were able to see just from the structure of the latent space that some materials seem to be thermoelectric and other properties. Now this is very surprising and a very interesting idea to use autoencoders or to use semantic networks and other things on large literatures. Another way is to have models that have a very interpretable output. So where you don't look into the models themselves, but the models itself gives you output that are equations, for instance, and there's some work on this in the field of symbolic regression, where you have a huge equation and can basically a huge complex data structure, and you can boil it down to simpler equations. Or, for instance, some graph representations I've shown in the first part, which are directly interpretable, where you can directly understand the results. Another method is interpreting the internal structures of neural networks. And there are also some very interesting research in this direction, where people, for instance, train the machine to predict some simple questions in dynamics in our solar system, and then when they look into the neural networks, they find out that the machine has actually made a switch from geocentric to heliocentric coordinates. So you can see actually some shift of coordinates that seems to be better for the machine to use. You can see them in the internal states of the neural networks. And a very different idea that I have basically not seen yet used in science is to observe the behavior of machines. And that could work in the following way. So imagine you have a space and you want to explore the space. And for instance, you want to find a quantum experiment with very high fidelity, or you want to find a molecule with a very high value of thermoelectricity or something like that. So now imagine the machine is exploring the space and is going to a direction of higher and higher of those values. But now it could be, or you could implement instead of those external rewards that you get actually from computing those materials, you could implement internal rewards. And those internal rewards could look like that the machine is motivated to go into a direction that it cannot predict itself very well. So for that, it would need additional additional neural network that can predict the properties of the structures that you are investigating, and then its action go towards those directions that it cannot predict very well. Those are actually locations that the machine will probably learn most about. So now, if you observe the machine while it is exploring this space, and you see that the machine will stick at some place and take several iterations to go away from a certain place, you can imagine that very likely this place was, for some reason, difficult or different to learn than all of the other things that it has seen before. So in a way, just by looking at the behavior of the machine, you can see places where there are difficult or new properties, physical properties of the space, and you can then look at those places and see what is going on there. And there are, I have more details and a reference to works that have been done in this direction in our perspective paper. Okay, now let me come to a conclusion. In the first part, I've shown that we now actually have in quantum optics some type of AI algorithm that can solve questions for or that can find solutions to open questions. And those solutions are presented in a way that we humans can basically immediately learn from them and understand what is the underlying reason why the solution works. So this is basically the furthest we can go. The furthest we can go. The next step would be that the machine is not only showing us the solution, but explaining us the solution. But this is still a few steps down the road. In the second part, I've shown you that we can actually predict in some way some part of what researchers will do in the future. And we can use this to create personalized predictions and also suggestions for new research directions that could be potentially useful for things like coming up with new interdisciplinary projects. Imagine you have a friend that works in some field that you don't know anything about, and your friend doesn't know anything about your field. Then you just put in your two research interests into this machine, and it suggests you what is the most reasonable thing that you two should work on that has not been worked on together. So that would be really cool if that works. And then in the end, we can think about what distinguishes us as human scientists from artificial scientists at this moment and in general. So, for instance, one could say that a human is creative, but if you have followed the latest release of DALL-E 2 and have seen those absolutely stunning pictures and artworks that it has created, that even won art contests recently, we could also say that the computer has some type of creativity, or whatever creativity means then. Now the only question is, how can we get this type of creativity into science? We could also say a human is curious, but what I've mentioned to you before, this intrinsic behavior, this intrinsic rewards, they are in a way a curious behavior. So the machine goes to directions that it doesn't understand very well. This is actually called artificial curiosity, or this whole type of research is called artificial curiosity. And in computer science, in reinforcement learning experiments, this has been implemented, and those systems can, for instance, solve the computer game of Super Mario without any external rewards, just by this intrinsic curiosity-based reward. So also artificial scientists could be curious. Now, the final thing is one can say a human can understand something, a machine does not understand something. But now again, the question is, what does it mean to understand something? If you boil it down, if you can actually come up with some description, it's very likely that at some point we will also have computers that mimic the thing that you call understanding. And we've outlined this in our perspective paper. Okay, then thank you for listening.
Thanks a lot, Mario, for this visionary talk, I would say. Unfortunately, the connection was a bit lousy, so at least I couldn't grab all things you said. But I mean, with the help of the slides, was enough to follow your reasoning. So, do you have questions for Mario?
Hello. Could you describe what the architecture was that allowed you to learn the quantum experiments? So you mentioned in machine learning, and you mentioned, you know, something, but what was the actual architecture?
We didn't use machine learning, and for those tasks, very often machine learning is not useful, or neural networks are not necessarily useful for those explorative tasks. That has been seen in many fields, like in the field of photonic material design, and also partly in chemistry. So as soon as you have a system where you can build up gradients, it is much more efficient to work directly in this system rather than abstracting this system. For instance, with a neural network. If I go back a few slides. So I think it's the last slide here. Yeah. So instead of using anything like a neural network, we use a physics-based, very abstract representation that is a huge weighted graph. Basically, also like a neural network, you have edges and vertices and weights, but it means something very different. And you can perform direct gradient descent on those systems and get out a parameterized solution. And afterwards, you can perform topological optimization to actually get the systems that you can understand as a human.
Okay, I see. Did you think of doing like a reinforcement learning approach, which is also good for optimization?
Yeah, I did a work that was between these first experiments that we have played on. The first algorithm that I've designed, which starts with optical elements to put on a table, I've applied a reinforcement learning algorithm with the other group. It turned out that it was not really better in discovering than okay, let me go back. So it was not better in discovering. So here, it was not better than in discovering than this algorithm, which is able to build up its own toolbox. So basically, I have some learning algorithm built in here, which is very concrete. I learned the useful components here, and then the algorithm can use those components. Now, if we compare this to a gradient-based method that I've shown then later, this graph-based method, if you think about what a reinforcement learning is doing, it is learning a policy that can solve a task. But here, I don't need to learn a policy to solve a task if I have access to the direct system, when I can directly apply gradient descent on the structure. So a reinforcement learning algorithm will, as far as from all of my experience, will never be able to outperform any design task where you have direct access to the system and perform gradient descent on the system.
Thank you. Thank you very much.
More questions? Renzo?
Hi. Sorry, a clarification on the second part of the talk regarding the metric that you use to basically establish that it predicts correctly the majority of the new topics that were explored in the 2022.
Mm-hmm.
Because like is that accuracy? I'm not quite.
Yes. Give me a second. Maybe I have an additional plot here. No, it seems not. So it's area under the curve. Do you know? Have you heard of this? Do you know? Okay. So what I'm doing is creating a ROC curve. It's receiver operating curve. So I'm sorting all of my predictions, and this is a standard method when you have classification tasks. And basically what I have is a classification task of the class of concepts that will be connected and that will not be connected. So I'm sorting all of my predictions from the highest predicted ones, so those that are likely connected, and those that will not be, that is predicted to be not be connected.
But like, do you have a kind of threshold to say that something is likely or not? Do you have a threshold, for example, between two topics?
Well, I can reformulate this number as a probability.
Okay, so you predict the probability, and then you say, yes, okay, likely or it's not. Okay, no, not this was the part that I'm okay. Thank you.
Okay, yes.
Okay, thank you.
Okay, other questions, comments? So if not, thanks a lot, Mario. And
thank you.